Okay, welcome to the first lecture of Artificial Intelligence. My name's Ian Reid. I'm going to be doing the first 7 or so of the lectures, and I'm going to hand over to my colleagues Gustavo Canero and Ling-Chao Liu, and I'll probably come back for the last 1 or 2 lectures. And you're going to be helped by us and ably by Fabod down here, who has previously done the course in tutorials during the course. I'm really disappointed because I wanted to start this lecture off with a really cool demo, and unfortunately my phone won't connect to Wi-Fi. I don't know if you guys have managed to connect your phones to Wi-Fi in this room, but I've got a technological problem. So I'm going to show you some demos at the end. I won't start with a demo though, but who is this guy? Presumably you all know who this person is. Anyone want to tell me? Alan Turing. So why have I got a picture of Alan Turing at the start of a course on artificial intelligence? Related to artificial intelligence, yeah, various murmuring. Father of artificial intelligence, father of modern computer science. We'll get there in a little bit. He was a mathematician and a logician. This is in the days when computers didn't exist. He helped invent the first computers. He was a cryptographer. There have been various films about him and so forth. But he also proposed the first idea of artificial intelligence. And we'll get to that a little bit later. I'm going to start with another photograph. Who's this guy? So why have I got a picture of Elon Musk at the start of an AI lecture course? Anyone want to hand up and I'll... Ryan. Well, self-driving cars, yeah, so he's CEO of, owns Tesla. Yeah? Yes, he owns or started OpenAI. Anything else? No, you're thinking of DeepMind. We'll come to that as well. Here's why I've got him at the start. He's been incredibly vocal about the dangers of AI. And I don't want to scare you all with AI. I just thought it would be interesting to note that this course, perhaps more than any that are offered at the university, is such a hot topic at the moment. AI is in the news all over the place, sometimes for good, sometimes for bad. Musk is one of the people who's out there saying, oh, we've got to be really careful about AI. I think actually a lot of what he says is overplayed in the press, and they love these headlines like, AI is highly likely to destroy humans. He's a master publicist. He knows that this brings publicity to his own companies and so forth. And actually what he's really worried about is whether Google and Facebook will monopolize it all. And that certainly wouldn't be good for his company and probably wouldn't be good for the world. Harder. Who's this guy? Anyone know who this person is? In his way, just as important as Elon Musk, perhaps not as good at self-publicity. This chap is, his name is Rodney Brooks. He's a South Australian. He went to Flinders. We won't cast aspersions on him for that. He then went to Stanford and MIT. He ran a very significant artificial intelligence lab. He was part of the Computer Science and AI Lab, CSAIL, perhaps the most famous AI lab and one of the original AI labs in the world, started in the 1950s. And he then left MIT. He founded the company iRobot, responsible for Roomba vacuum cleaners and so forth. And he founded, I can't remember the name of the company, something like Personal Robotics or whatever, that makes Baxter and Sawyer, various human-safe robots. And the reason I've got him up here is that he's written a really nice blog article, and I'm not going to go through the blog article now, but sort of a response to some of the hysteria that you hear about AI. He called it the 7 deadly sins of predicting the future of AI, and he goes through and lists the ways in which people, typically the press, but not entirely the press, will overblow either promises or dangers of AI into the future. So I just encourage you to go away and have a read of that article. Once I put these, I think I've put these slides up on the course pages, and so you'll have access to that link later. Before I dive into what is AI, I want to do the other boring stuff that we have to do. if I can. Okay, so you get presumably slides like this at the start of every course. Most of you are third year, and therefore you know the form already. Here's the detail for AI. There's going to be 4 assessed components, a written examination worth 55% at the end, and 3 assignments worth 15% each. If you spoke to the students from last year, you will have heard that the assignments perhaps they felt were a bit mathematical, lots of writing and mathematical proofs. My hope for this year is that we'll have something a bit more practical, some implementation work for you to do. Obviously, lectures and tutorials. I encourage you to come to all of the lectures and tutorials. Some of the material at times may seem a little bit dry. We'll try and spice it up, but please bear with us. And there'll be tutorials that cover material. Good reason for going to the tutorials, even though they're not assessed, is that a typical tutorial question will be a typical exam question. Okay? So if it's in the tutorial, it's pretty much fair game for exams and about that standard of question as well. But we can talk you through that in the tutorials as well. As with all these courses, there are minimum performance hurdles. The hurdles in this case are going to be the exam and assignments 1 and 3. That's not a reason for not doing assignment 2. It's just that if you fail to do assignment 2, you won't fail the entire course. Whereas if you fail to do any of these and reach your 40% minimum, you will fail the entire course. So that's the standard blurb about minimum performance. And I'm sure you've seen all this stuff about grades and what have you ad infinitum. How many people here are doing masters, doing the 7,000 course? Okay, so there's a few of you. It's not my plan at this stage to set anything particularly different, but I will put optional things in the assignments. Okay, and my expectation is that if you're a master's student, you will definitely make an attempt at the optional components of assignments. That's really going to be the only difference in terms of the 3,000 course and the 7,000 course. And I guess you guys have been around long enough to know the late submission policy, although perhaps if you're masters and you're new, then this is the standard late submission policy that if you submit a day late, then your mark is capped at 75%, 2 days late capped at 50%, 3 days late 25%. This is generally speaking a blanket rule, but as you all know, in exceptional circumstances, we will take things like being sick and so forth into account with suitable evidence. Okay, so I'm not going to go through any more of the boring stuff. I'll put those slides up. You've probably seen them all before. Yes?
Most of the assignments have resubmission, like before the due date can you submit all the time?
To be determined. Okay? And it will depend on exactly what the outcome is. If it's a programming exercise and there is an answer and there's a way of testing your program, then yes, there will be resubmission. Okay, it's going to get a little dry for a few minutes, so bear with me and I'll show you some cool stuff at the end of the lecture. So what is AI? You probably, because it's been in the news so much, you probably have some conception of what it is already. So it's a scientific field which strives to understand how humans think. And it's a relatively new field. The term itself was only coined in 1956 at a meeting in Dartmouth. For our purposes, I guess the most important definition here is that AI is attempting to build intelligent entities. And even that definition is a little bit open to debate, because what do we even mean by intelligent? There's a fantastic book, sorry I'm going off script here, fantastic book called Gödel, Escher, Bach from the mid-1980s that talks a lot about intelligence. And also around about that time people were starting to build good chess-playing robots. And at the time, perhaps in the mid-1950s, early 1960s, it was thought that if you could build a great chess-playing robot, something that could beat a human, then you would have achieved intelligence. And then as soon as we could build systems that could beat humans at chess, it was just like, well, actually, that wasn't intelligent after all. That was just really fast search. We're going to cover search later on in the course. But so what is AI? 4 schools of thought that we'll talk about now and then hone in on a particular definition for this course. But so systems that think like humans, systems that act like humans, systems that think rationally, or systems that act rationally. And that sort of depends on what you think is most important. Is it most important to address behaviour? And if we're addressing behaviour, does the behaviour seem intelligent? Then we're probably thinking about either systems that act like humans or systems that act rationally. On the other hand, if what we're interested in is thought, and we think of intelligence as being intimately connected with thought processes and brains, then we're probably up here, systems that think like humans or systems that think rationally. So if we unpick this axis here in the columns, then how do we measure the performance of something like a human? Well, we're going to measure our success in terms of fidelity to the way a human behaves, or to human performance. On the other hand, if we're thinking about an AI system in terms of rationality, then we're probably measuring its success against some ideal concept of intelligence that we're going to call rationality. And the two, acting like a human, thinking like a human, or thinking rationally, acting rationally, not always exactly the same thing. Often they are, but not always. So let's go into a little bit more detail about each of these. I don't like this word, thinking humanly, but just stay with me for a bit. So the aim is to create systems that think like a human. But to do that, we need to be able to work out how humans think. And so we could do this via one of a couple of ways. One is via experiments, psychological experiments that are going to treat the thought process as a black box and make observations, try and understand how the thought process is working by understanding those observations. That's a sort of an external way of understanding. The internal way of understanding would be to do something like functional magnetic resonance imaging of the brain. So you ask a person to do something, and at the same time you're monitoring the activity that's going on in their brain and try to understand how the brain is behaving in that way. And then we'd express those findings either through a software program or in hardware. Typically, this definition of AI, or people who are interested in this, are more concerned with accurate reproduction rather than necessarily solving a particular problem. And we're computer scientists. This is all really, really interesting stuff, but as computer scientists, we probably want to solve problems, so we're not going to spend too much time on this particular definition. Back to that guy, Alan Turing, although that's not Alan Turing, that's Benedict Cumberbatch. But has anyone seen this film? Okay, so there's a number of films about Alan Turing. There's also a fantastic book called whoops, I've gone too far, called The Enigma of Intelligence. I encourage you to read that if you have the muse. But this film, and many of the films about Turing, focus primarily on his role in cryptography, in cracking the Enigma code during World War II. But actually what's most important for us in the context of this course is the title of this film here, The Imitation Game. He proposed a functional definition of artificial intelligence. Oh, by the way, I can't do the demo, but what I really, really wanted to do was bring up my, well actually, I can do the demo on 4G. And you might have to be quiet. We'll see if this works. Okay, Google. How old was Alan Turing when he died?
Alan Turing was 41 years old when he died in 1954.
Okay, there you go. So what a cool demo of AI right in front of you. This is stuff that has come out just in the last few years. Speech recognition has been one of the great successes of AI. That's speech recognition, that's parsing the sentence to understand what it means and so forth. These are all things that have been done in AI. You come out of here with a great AI degree, then Google and Facebook, whatever, are going to snap you up. We hope they don't, but... okay, so... Turing proposed this test, now known as the Turing test. And the reason why it's really interesting is that it provides an operational definition of AI, and it avoids this sort of debatable definition, qualifications, and so forth. Basically, it says that an entity is deemed intelligent if it passes a test. And the test is that if a human interrogator posing some written questions cannot tell whether the written responses came from a human or not, then we're going to say it's artificially intelligent. So there's a depiction of this. We've got a person behind a screen typing something. Of course, Turing perhaps didn't know, well, wouldn't have known at the time that he'd be able to talk into a mobile phone and that would potentially be understood perfectly. So he could have had a test that was talking through a screen. Maybe in years to come it will be just talking to an entity. We'll go all Blade Runner on you. Okay, another definition. AI is thinking rationally. So this is concerned with the reasoning process, laws of thought and logic. And part of the reason why this is attractive is that there's a whole mathematical framework associated with logic that's been around for many, many years. So given a problem and a set of circumstances, we want to be able to reason logically to the conclusion that a given action is the correct action with respect to some goal. And so this provides formal terms and notations to describe and solve problems, which is great, except that not all problems can be formalised using standard notations. And also sometimes implementing the solutions that pop out of the maths is computationally very, very expensive. I said a couple of minutes ago that thinking rationally and thinking like a human were not necessarily the same thing. Let me give you just a couple of examples of why that's not the case. Mainly, humans think rationally, but sometimes our eyes can deceive us. Perhaps, well, the rational person, I don't know why here we go. The rational person knows that these lines here are parallel, but we don't see them as parallel. The rational person can cut this circle out and overlay it on this circle and see that they are exactly the same size, but we don't see it like that. So there's a whole bunch of reasons why we're not rational all of the time. Perhaps it's because there's no provable set of actions, provably correct set of actions. We're affected by emotion, we're affected by perceptual aliasing, issues that I've just shown, that we don't necessarily perceive the world exactly as it is. Sometimes the best action needs to be a reaction. You don't have time for introspection and logical reasoning, you just have to respond. So humans don't always respond in the most rational way. And then the final definition that I wanted to touch on is this one of AI acting rationally. So an agent, and we're going to spend some more time in the next lecture talking about what I mean by an agent and formalising that definition, but for these purposes, an agent is just a sophisticated computer program that takes some inputs and produces some output. It may be physical output, it may be just numerical output or some graphics or something like that. And a rational agent, under this definition of what an agent is a program that acts so as to achieve the best outcome, or, when there's uncertainty, the best expected outcome. Okay? If we don't know the exact consequences of the outcome, then typically what we would do is rely on expectation. We would try and quantify what the possible, the likely outcomes are, how probable is each of them, how much reward will we get for doing each of them, and choose the one that maximises utility. And I'll come to a formal definition of that later in the lecture course as well. But so here's our agent with some means to interact with the environment via actuators, some means to sense the environment, and some program in here that's processing all of this. So the percepts are things that the sensors see from the environment, the actions are things that the actuators perform back on the environment. There are some advantages of having this as our definition of AI. In particular, it's more general than a laws of thought approach because we're not confined to logical terms and notations. It's also, and I come back to this notion that we're all computer scientists, it's more amenable to a scientific or an engineering development than the thinking humanly. If we can create a program that can have certain effects, it doesn't really matter whether it mimics the brain or not. And so we're mostly going to follow this definition of AI in this course. I guess that there's another one here that will tie into some stuff that we talk about later on in the course. We will be talking a little bit about logic and about probability and so forth that ties in with the thinking rationally aspect. We're also going to be talking about how many people in the room have heard of deep learning? Okay, so quite a number. So there will be some lectures on deep learning. Yes?
If there is a difference, how would you define the difference between machine learning and AI?
So I would say that AI is a more general subject than machine learning. Machine learning is the thing that has brought AI into the next level of performance. So one of the things, my own research and the research of a number of my colleagues is in computer vision, which has been very heavily influenced by machine learning. And one of the things that the people tried to do in computer vision was to understand how stuff worked and build algorithms for particular inputs to particular outputs. A classic example is face detection, for instance. And for many years, up to around about the mid-1990s, late 1990s, people were trying to build a program that understood how an eye and a nose and a face was all put together and code that and then be able to detect a face. And in the late 1990s, along came the machine learning people and said, actually, the best way of detecting faces is to show a generic machine learning system millions of faces and millions of non-faces and get it to distinguish between the two. And then run a detector across an entire image and say, is there a face here, is there a face here, is there a face here, is there a face here? Works brilliantly. So much so that within 12 months of that algorithm being published, it was in commercial products. I was able to buy a Fuji F31FD, which was one of the first cameras that had face detection built in. And that came directly from some machine learning research. Sorry, I'm getting a little bit distracted here. But so machine learning is the thing that has taken AI to the next level. People have been working on AI through looking at logic, building ontologies, thinking about representations, and all of that kind of stuff. But what we've learned in computer vision, and they've learned in AI as well, is that quite often it's very difficult to hard code knowledge. Sometimes it's much easier to have a generic system that can learn that knowledge by looking at lots and lots of data, and that's what machine learning does. Machine learning will look at data and make inferences from that data. Does that answer the question? Okay. AI, big, machine learning, this big, but now almost as big, okay? So machine learning is really overtaking. And sometimes you'll hear people use them interchangeably. We're going to do a bit of machine learning in this course and a bit of more traditional AI. And I believe next year there's a statistical machine learning option that you can take as well. Where was I? Okay, so we're mostly going to follow this acting rationally. And so coming back to my little aside, I asked how many of you know what deep learning is. And part of the reason is that deep learning has revolutionized artificial intelligence and machine learning in ways that are just phenomenal. In 6 years, the field has gone from not really working to something that is being invested in billions of dollars by various governments, trillions of dollars by various governments around the world. And it's not just governments, it's big companies like Google and Facebook and so forth. But we don't really understand what's going on inside one of these deep networks. So unlike a sort of logic introspection, where you're doing your inference and you can trace it back and understand why a decision was reached, You get an output at the back end of your black box deep learning system. You don't really understand how that answer came about. And if you're just interested in acting rationally, in a sense you don't care how that answer came about as long as it's right. There are some people that do care, and maybe we'll touch on that later on in the course. But for our purposes, this acting rationally definition is going to be the most useful one. A little bit more background. AI has really been influenced by and drawn on a whole bunch of different fields. So in philosophy and mathematicians have developed formal methods for logic reasoning and so forth. In philosophy, people think about the mind as a physical system, the foundations of learning, language, communication, rationality, and so forth. There's a whole formal definitions in mathematics for proof of algorithms, for computation, undecidability, intractability, probability theory. All of these things are really relevant to artificial intelligence, particularly if we're trying to represent uncertainty. In economics, so economics and mathematicians and mathematical economists develop utility theory and decision theory. What is the best decision to take at any one time under a certain amount of information, under certain expectations of how the world is going to play out. Neuroscience, particularly to do with trying to mimic the human brain, understanding the physical substrate, understanding neurons, and deep neural networks are actually just a very simple replication of a very simple mathematical model of what's going on in the brain. Psychology, phenomena of perception and motor control, particularly in the early days at CSAIL and MIT, people were very interested in understanding optical illusions and whether that could influence the way that we built algorithms for doing visual perception, which is intricately related to artificial intelligence. Obviously, computer engineering and building fast computers. Control theory, so something for the engineers out there, designing systems that maximise a particular objective function over time, which is basically what control theory is doing, and minimising uncertainty while you're doing so. And linguistics, so knowledge representation, grammar, and so forth. I mentioned that it was a fairly new field. So really the first people to even think about modelling the brain back in 1943, when computers were effectively just being invented. I've got the date wrong there. I'm going to have to fix that. So Turing's computing machinery and intelligence. I think that actually should say 1953. But I'll fix that before I upload the slides. I mentioned that the term AI was coined at this meeting in Dartmouth in 1956, where a bunch of people who were interested in this got together and had a workshop about it. And in the 1950s, people looked at building early AI programs, typically things like simple, deterministic things like checkers, Newell and Simon's logic theorist, and so forth. 1965, Robinson proposed an algorithm for logical reasoning, and then we had things like Prolog come along subsequent to that. In the 1960s and early 1970s, AI discovered computational complexity and realised that this was potentially going to be a significant barrier to progress. But people had thought about neural networks, and by, say, the mid-1970s, a lot of it had almost disappeared because it just didn't work terribly well. We'll come back to that in a little bit. Around about that time also, people were building what are now, what were then known as expert systems. Has anyone heard of a system called MySyn? Okay, so I can't even remember what MySyn does. It was something to do with drug diagnosis. Actually worked very, very well. It worked so well, in fact, that they thought they might be able to roll it out, but then couldn't because no one could decide who would be legally liable if it did the wrong thing. And then sort of faded away into obscurity. And systems like that, not based on the same technology, but the same idea of doing medical diagnosis, are now raising their head again, where we can build deep neural networks that can detect a cancerous growth, or you can point a phone at your at a mole and it can tell you whether that's skin cancer or not. AI started to become an industry in around about the 1980s. There was a resurgence of neural networks, and then that fizzled out again. Because they still didn't work in the mid-1980s. We started to see another type of intelligent agent come to the fore. Sorry about that. I was never a game player, but I bet some of you guys are game players, and you will know that you expect the entities in your games to behave in an intelligent fashion. And so building AI for games became a huge thing, starting around about the mid-1990s. And then I've already alluded to it, 2012, Deep Network wins the ImageNet Challenge. There's a famous paper from 2012 published at a conference called NIPS, Neural Information Processing Systems, where for the first time, one of these neural networks was able to outperform other algorithms at doing an image recognition task. And it didn't just outperform the other algorithms, it blew them out of the water, so much so that if you look at the number of papers that are published on deep networks in my area, computer vision, and in machine learning conferences, it's gone from a handful every year to a handful that are not about deep networks every year. Yeah?
You said that with deep neural networks, it's difficult to actually understand what's actually giving the result.
It's difficult to understand why it's given you a particular result, yeah.
If you were using Boolean circuit type structure for a neural network, because it's Boolean, then couldn't you go backwards through the logic to find out what it's doing logically?
Well, you potentially could, but you could, and you could do that with any system. But the issue with the neural network is that tracing your way back, you're tracing your way back through 1.5 million parameters. Almost impossible to say exactly what is the influence of this particular parameter on the outcome. It's to do with the complexity of it, not whether it's deterministic or not. The net itself, give it the same input, it will give you the same output. Although one really interesting thing, and again I'm getting slightly distracted here, but I've got a little bit of time up my sleeve for this lecture. There are some really interesting papers that show that if you take an image, maybe it's an image of a lion, and show it to the deep neural network, it correctly predicts with high confidence that it's a lion. Make some very small changes to the image in a particular way, in a particular direction, imperceptible to a human, show it to the same network, and it will come out and say with very high confidence that it's a dog, not a lion. Okay? So, and it's very difficult. One of the reasons that people are trying to build those adversarial examples is to try and understand what's going on inside, and we don't properly yet. So, state of the art in AI. These slides were originally written by my colleague a while back. You'll also find that some of it is drawn from Stuart Russell's excellent book, AI, A Modern Approach, which the latest edition has quite a bit more about deep networks. The original edition, AI, A Modern Approach, really didn't talk about neural networks in much detail at all. They might write the book rather differently now. But so what is the state of the art? Well, the state of the art is that computers routinely beat humans at chess. Garry Kasparov, world champion, was beaten by IBM's Deep Blue. I think that was around about the mid-1990s that happened. Autonomous path planning and navigation. So the whole self-driving car thing that you read about, we already had that raised through Elon Musk and Tesla, so forth, came about because the defense funding agency in the US, DARPA, set these grand challenges. They said, can you take a car out and drive it outdoors for several hundred kilometers? Or then the following year they said, can you drive a car around an urban environment? So this was the DARPA Urban Challenge in 2007, 96 kilometers with traffic. And they built vehicles a little bit like this. The winning team got purchased by a small company that then got swallowed up by Google and became the Google self-driving car outfit. And self-driving cars are now a reality. They may not be on our roads right at the moment, but they are a reality. So AI was even used in the first Gulf War. We go back to the early 1990s, and the US troops were using this thing called DART, Dynamic Analysis and Replanning Tool, that was developed using AI, trying to make smart decisions. And the idea of this was that it was trying to distill a whole bunch of information to be able to make decisions in several hours for problems that typically would require several weeks of analysis. Robot-assisted surgery is now becoming a reality. So some systems are using computer vision to understand what's going on, to generate 3D models of internal anatomy, to guide doctors and so forth. And you guys will be encountering AI in your everyday life, I guess. So I've already mentioned one. How many are game players? How many don't want to admit to being game players? So some of you have already encountered a lot of AI in those games. Okay, so this is an old slide. The office assistant. I don't think that annoying paperclip even exists anymore, does it? How many people have seen the annoying paperclip in Office? Okay, so shows the age of most of the audience. It was one of the most annoying things about Microsoft Word. Every now and then this paperclip would pop up and say, I think I know what you're doing, can I help? And inevitably, well, I never asked it for help. So now we've got speech recognition, and that speech recognition really can help. OK Google or Siri. We now have robot vacuum cleaners. So this down here is the Dyson 360i that uses some mapping technology and some smart navigation technology developed by my postdoc Andrew Davison at Imperial College. Face recognition is now de rigueur. I talked about face detection going into cameras using AI, using machine learning. Face recognition is now de rigueur. If you use Google Photos or Facebook, it will automatically tag people because it recognizes them. So this is all, admittedly, with a bit of a lean towards the computer vision stuff that I do and a lot of my colleagues in Adelaide do, but this is all AI stuff. I thought I'd show you another cool video because this just came out. Yes, or it came to my knowledge yesterday. So this is a system developed by my colleague, well, partly by my colleague Frank Delert at Georgia Tech. Some of his students started this company. It's a company called Skydio. Anyone heard of Skydio? So this is their first product, just launched. I think there are going to be some captions in a second that Okay, so this is AI research and products that is happening right now. Okay, I'm not going to show you any more of that cool stuff. You can go and find it yourselves. Go and buy one. If you do, let me know, because I would love to play with it too. What's going on? Okay, so course outline, and then I'll finish off with some more cool stuff. But just so that you know what to expect for the rest of the course. I'm going to cover a lot of traditional AI, certainly in the first 6 lectures, stuff about search. And then we're going to go on to deep learning, and then we're going to go on to probabilistic stuff. And part of the reason for doing the original search stuff is that although deep learning has revolutionized AI as a field, quite often the most significant advances are when people combine the traditional stuff with the new stuff. And a really great example of that we will go into in a little bit of detail, not much detail unfortunately, is AlphaGo. How many people have heard of AlphaGo? How many people have not heard of AlphaGo? Okay, okay. So for the benefit of the three people up there, AlphaGo is a Go playing program built by a company called DeepMind. It's a London-based acquisition of Google, so it's now Google DeepMind. And they combined deep learning with traditional methods of search to build a Go program, which is considered to be the most complex board game, so outstripping chess by orders of magnitude in terms of the size of the state space. And for the first time, I guess it was 2 years ago, they beat a world champion. And it was, I was fortunate enough to be giving a lecture on Monte Carlo tree search, which we will do in a few lectures' time, a week after this happened. So able to bring that into the classroom a week after it happened was absolutely fantastic. So we'll talk about that. But that's one of the reasons for covering maybe what you might consider dry 1980s or even 1960s artificial intelligence, because bringing those techniques together with deep learning can have some of the most powerful consequences. So these are the broad topics. I'm going to cover a bunch of lectures on search and game playing, and then Gustavo Canero is going to talk primarily about classification and learning, building up to deep learning, and then Lingqiao Liu will talk about how we deal with uncertainty and probabilistic reasoning. And like I said, the combination of these two has led to AlphaGo. The combination of these two has led to some really cool stuff in single view depth estimation, for instance. And finally, just a bit of an advert. This is not just a course of us sort of pushing some information at you. There really is an incredibly strong and active group working in particularly computer vision, but AI and machine learning in general at University of Adelaide. So much so that we have recently, as of the 1st of January, created the Institute for Machine Learning that really subsumes the former Centre for Visual Technologies that does some very cool stuff. As a measure of this, and if you want to talk to me about any of this, do come up to me offline, or we can talk about it on the forums and so forth. But so for object recognition, being able to recognise a bunch of objects, and I wanted to be able to show you that on my phone. I will put a link to a demo. What I'm going actually, no, I won't do it. I can't mirror it up here, but we do have a demo server where you can take a photograph and ask it to identify the objects in the image, or create a caption for that image. Some of my colleagues have got into a task called visual question answering. Look at an image and ask the computer questions about the image. And they obtain first place. This is a competitive space. Google and Facebook and Amazon and these companies are all operating in this space. With our colleagues at QUT, we built some segmentation software, so that's what's going on down here, and used that to do object picking, and won an international competition, the Amazon Robotics Challenge. And part of the reason for showing you this is using the same technology. It's not the Amazon Robotics Challenge robot. This is just one that we have in the lab. But I'm showing you this partly because one of the undergraduates who helped put this together over the summer is in the lecture today. So what this is doing, it's recognizing those objects, it's planning a path to pick them up, and it's moving them around. The reason Amazon's interested in this is because although they own more mobile robots than anyone else on the planet, their mobile robots they pick up shelves and they move them from a storage place to a person. And then a person does the hard stuff of recognizing objects. Just want to show you a couple more videos. You wanted to ask a question down here. So one of the things that we're interested in potentially is recognizing and segmenting scenes. So if I can find my... So this was developed by one of our postdocs, Guoshen Lin, and what you're seeing here is a state-of-the-art system for labelling every pixel in a video stream. So the different colours are representing different classes in the world. So this slightly purpley grey colour is road. The blue is car, red is a pedestrian, yellow is a road sign, orange is a traffic light, and so on. And as you can imagine, being able to understand and label what things are in the world is every bit as important as understanding the geometry of the world. So this is a semantic understanding that is crucial for being able to navigate in an uncertain dynamic space. Lots of other examples. I think what I'll do is, if you get to the lectures early, I'll try to show you a few other examples of cool stuff that's going on here, so that it doesn't impinge on the time for the lectures. But I got time. You had one question. Did you want to ask? Or?
I was going to say that Amazon's object detection would also be used in Amazon Go stores, wouldn't it?
Yeah, absolutely. So in fact, Amazon is, for those who don't know, Amazon has just launched a supermarket where you go into the supermarket and you just pull stuff off the shelves, and it recognises all of the stuff that you're putting into your trolley, and you walk out and it automatically bills you for it. This is stuff that's heavily reliant on computer vision, heavily reliant on AI. In fact, one of the guys that was helping develop it, Steve Gould, is a colleague of ours that we work very closely with from ANU. He was on sabbatical there last year, just before the launch. So yeah, same idea, same technology. Good, thank you. See you on Wednesday. Good.
My name's Clint, by the way. I'm in my penultimate year. I'm doing an electronic electrical and mathematics science, obviously. I'm interested in neural networks, how to actually implement them more efficiently in hardware, specifically FPGA. Over the holidays, I'm mucking around with TensorFlow, and I found a way of kind of tricking TensorFlow into training neural networks that have Boolean outputs, which you should be able to do with backwards propagation, but I've figured out a way to do it. And that, of course, means that you're simplifying, you're removing the hardware that you need for creating an activation function, or you're actually removing the software side of things if you're doing it on a computer as well. So I've got to a stage where I've got some basic tests that work. The XOR test works. You've probably heard of the Monks tests. Okay, there are some earlier tests that used to be used before MNIST. I haven't done MNIST. Okay. And it seems to work. The only thing now is, like, now that I've got something working, I'm not sure what can I do with it. Yeah. But, yeah. And it is, I mean, I have got an idea of actually how to expand the system further, but I'm not sure what to do with what I've learned so far. If it's something that's worth writing a paper, or is it something that I should keep aside to start a, if I do get to a PhD, to do that, or I don't know.
Yeah, on the basis of that description, I can't give you a sensible answer. Yeah. But what I'd suggest is, if you wrote it up, not as a formal paper, but just as sort of blog-style post, a little bit of detail, and then maybe give it to me to look at, or give it one of my colleagues, perhaps Chun Wai Shen would be a good person to look at it, and he'd be able to tell you whether there is something positive. There's a fair bit of work that people try to finalise that.
Because I know usually things run through the GPU, if you can make it more efficient, using an order of magnitude as power.
There are a bunch of people around the world who are thinking about FPGA. We're thinking
Wait a second. I'm going to talk to Ian about